everyone. Welcome back. And for our second talk today, we're very happy to have Jane Coons joining us from University of Oxford. And she'll be speaking about vanishing ideals of symmetrically colored Gaussian graphical models. So thanks, Jane.
Thanks. Yeah, thanks so much. It's such a pleasure to be here. So thanks very much to the organizers for inviting me. I'll be talking about a paper with these co-authors, Aida Marai, Pratik Misra, and Stefana Soraya, mostly about a paper with a very similar title called Symmetrically Colored Graphical Models with Toric Vanishing Ideals. So most of what I'll talk about today is a lot of toric stuff. And then towards the end, I'll talk about some forward-facing work on these ideals more generally. I'll start with a little bit of an overview of algebraic statistics. So some of this might be a repeat of what Carlos talked about, but I hope it'll be helpful for some people to hear it again. So the core idea, or a core idea in algebraic statistics is that we take statistical models, so by that I just mean a set of probability distributions or density functions, and we think about them as algebraic varieties. So these are often either parametrized or restricted to satisfy some conditions, and in many situations you can translate this into the vanishing of some polynomial equations. And our goal is to use these classical algebraic geometry techniques to try and learn statistical information about your model. So it's a little bit of a dictionary, a couple of examples here. In statistics, you might think about discrete log linear models. But on the algebraic side, if you take the Zariski closure of one of these things, you just get a toric variety. You can use toric geometry stuff to learn about it. The type of models I'll be thinking about today are linear Gaussian concentration models. Could also have linear covariance models. So this is where you're putting linear restrictions either on the covariance or the inverse covariance concentration. And these are linear spaces of symmetric matrices, right? They're just symmetric matrices with some linear restrictions on them. And you might also, if I know about the concentration matrices, I might ask what are their covariance matrices. And so then I'm inverting this linear space of symmetric matrices. That's mostly what I'll be talking about today. And so yeah, the core idea is we can use algebra, geometry, and combinatorics to get some statistical information about these models. Okay, so I'll probably breeze through this because Carlos really talked about this. So I have an n-dimensional random vector, and I say that it's distributed according to a multivariate Gaussian distribution with mean 0 if it has this probability density function where sigma is positive definite, and that's the covariance matrix. Everything I think about today is going to have mean 0. Of course, you could write this down for any mean that you like. So this positive definite sigma is the covariance matrix, and its inverse is called the concentration matrix for this density. And so of course you can think about the set of all such densities where the covariance matrix is restricted in some way, that's a statistical model, but I'm going to sort of conflate that today with just the set of all of these covariance or concentration matrices and call that set of matrices the model as well. And that's the thing I'll be asking algebraic questions about. So if I fix some linear space of symmetric matrices, then the linear concentration model that's specified by that is just the set of all multivariate Gaussian distributions with mean 0 and whose concentration matrix, so the inverse of this covariance matrix, lives inside of the linear space intersected with the positive definite cone. Okay, did that go away? Whatever that, yes, okay, great. And so again, the statistical model you could think of as the set of all of these Gaussian distributions, but equivalently, I'll just think about it as all of the concentration matrices. Okay. I'll talk a bit about graphical models now before we get to what I mean by colored graphical models. So I'll fix a simple graph whose vertex set is, say, 1 through n. It's got some edge set. And this specifies a linear space of symmetric matrices as follows. So it's all of the symmetric matrices whose ijth entry is 0 whenever ij is not an edge in my graph. So it's just placing some 0 restrictions on your concentration matrix. And then the Gaussian graphical model associated to this is the linear concentration model defined by this linear space of symmetric matrices. And the interpretation that you can have for this in your mind is that if two vertices are not connected by an edge, then they're independent of each other given all of the other vertices. So that's kind of where this comes from. It's giving conditional independence constraints on the different random variables at the vertices. So for example, if this is my graph, this is a graph you're going to be seeing a lot of over the next hour or so. The only missing edges are 1, 4, and 2, 4. So those guys get zeros in my matrix, and then everything else is free, except for it has to be symmetric, but you know, the upper triangle here can be whatever you'd like. Okay. Any questions just about graphical models? Please, there's plenty of time for questions sort of built in, so if you have questions, please ask.
Does it also need to be positive definite?
Yeah, great question. So for, yes, you're right. So I need, if I actually want to get a multivariate Gaussian, I would definitely need this to be positive definite. However, since I want to do algebraic geometry on this stuff, I'm going to take the Zariski closure and consider the whole linear space. Yeah, great. Awesome. Okay. So now I'm going to add colors to this graph. So I'm first going to color both the vertices and the edges, but I want to use different colors for both of those things. So I don't want any vertices to have the same color as an edge or something like that. I'll always use regular G to denote the underlying uncolored graph, and fancy G is the colored graph. And my notation is that lambda of a vertex or lambda of an edge is the color of that vertex or edge. And this also gives me a linear space of symmetric matrices in sort of a similar way. So I have these same 0 restrictions that Kij is equal to 0 whenever ij is a non-edge, but now I'm also adding equalities. So for two vertices with the same color, I need that their entries in the concentration matrix are equal. And the same thing for two edges of the same color. Okay. So here, for example, vertex 1 and vertex 2 have the same color, so K22 also has to be equal to K11. Similarly for the edges 1, 3, and 2, 3, they've got the same color, so those two guys are equal. And I still have these zeros in 1, 4, and 2, 4. This is kind of adding some symmetry to the model, where I think that maybe for two vertices, they're behaving in a similar way. They have the same concentration. So if I think that there's, for some reason for my setup, that there's some symmetry, I can encode it using this graph coloring. Okay, so the colored Gaussian graphical model is just either all of the multivariate Gaussian distributions whose concentration matrix lives in this linear space intersected with the positive definite cone, or just the linear space itself. So I've described all of the concentration matrices in this model, but I also might want to know what the covariance matrices are. That corresponds to inverting all of these. So if I have any linear space of symmetric matrices, or indeed matrices in general, I can write down its L inverse, which is the Zariski closure of all of the inverses of matrices that were in the original linear space. And in our setting, this inverse linear space intersected with the positive definite cone is exactly the covariance matrices that arise in my model. And so you can ask all sorts of questions about this. For me, I'd like to know what the vanishing ideal of this inverse linear space is. And in particular, when is it toric? And if it is toric, can I give a generating set or Markov basis for it? I think this is a really interesting algebraic question. I'll motivate it a little bit and then get to the fun algebra. So where do these show up? These colored graphical models are pretty widely applicable, especially in like the biological sciences. They've become pretty popular. So they're used for gene co-expression networks to model interactions of genes within a cell. They're especially helpful when you have like a big network because they reduce the dimension significantly. So for standard graphical model, the dimension is the number of vertices plus the number of edges. But when I add colors, I can make this very low dimensional because the dimension just becomes the number of colors that you use. So it can make really big problems like this more tractable. Dynamic regulatory networks. I thought this one was cool. These authors used a colored graphical model to model like how different factors affect attitudes toward climate change and similar, so it's like about environmental psychology. Cool, okay. And why do I care about the vanishing ideals? Well, they're useful for a lot of these maximum likelihood estimation problems. So especially in the case of linear concentration models, you can compute the MLE by taking this variety of the covariance matrices and intersecting it with an affine linear space that's specified by your data. And so having the vanishing ideal, I think you can see why it would be useful for this. So it helps you, if you think you have a closed form expression for the MLE, you could prove that that works. Or more realistically, you could count the number of critical points of the log likelihood function using this ideal, and that's the ML degree of your model. So, if these also find applications in model selection, so there's this popular tetrad procedure for causal inference that uses the quadratic binomials that live in this vanishing ideal to infer your graph. And the graphs that I'm going to talk about for most of today are toric and quadratically generated. So actually, this is all of the things that you can want to use in the tetrad procedure. Okay, great. So here's the main theorem, and you won't know what most of the words in it are, but you will by the end of the talk. So I'll let IG be the vanishing ideal of this inverse linear space. And here's our theorem, that as long as this G is an RCOP block graph, so those are the two things that we don't know yet that I'll define, but it satisfies some conditions, then this is a toric ideal and it's generated in degrees 1 and 2. Okay. And in fact, we give a generating set for this for this ideal that uses the uncolored graph and some complete graph that we get, some colored complete graph that we can get from this G. Okay, so now we need to know what an RCOP graph is and what a block graph is. Okay, but first here's an example. So this one that I showed you before, you'll soon see, satisfies these conditions. And here's the vanishing ideal. And I think they sort of make sense. So the color of 1 is equal to the color of 2. Okay, so sigma 1, 1 minus sigma 2, 2 is there. That's nice. Similarly, these edges have the same color, 1, 3, and 2, 3. This one's sort of interesting. 1, 4, and 2, 4 aren't edges, but they should still be equal to each other. Something a little bit different. And then we get this quadratic, which will...
Yeah, so in the inverse, they're equal, I guess, because that's the function.
Yeah, exactly. In the inverse, they're equal. But this won't always be true for any colored graph. It really depends on this special coloring condition.
Yeah, I guess you can see like the cofactor is pretty much the same.
Mm-hmm. Yeah, right, exactly. So, but it won't be in general for an arbitrary colored graph. But in this case, that's exactly right.
You're saying in the inverse, in the concentration matrix, 1, 4 is equal to 2, 4 too?
Well, in the concentration matrix, they're both 0. So yes.
Oh,
but
yeah.
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 But that's not the point.
Yeah. Yeah. Cool. Any other questions?
And the last one, what does it mean?
Yeah, so here's so one way of thinking about it is that if I walk along from 2 to 4, it's really important that there's only one way to do that here. I'll talk about that in a bit. Then it's like, the colors that I use going from 2 to 4 are exactly the colors that I use going 2 to 3, and then 3 to 4. And that's sort of, and then and stopping at 3. So this is like go to 2 to 4, and then add 3, or go 2 to 3, stop at 3, and then 3 to 4. Yeah.
What do you mean there's only one way to go from 2 to 4?
Shortest way. Yeah, good question. Okay, there's yeah, sorry. This will all be made clear in a couple of slides. Okay, so first of all, what does it mean for a colored graph to be RCOP? So this is a condition on the coloring. This was introduced by Høsgaard and Lauritsen in 2008. So this graph is called RCOP if there exists a subgroup of the automorphism group of your graph, such that the edge and vertex orbits are exactly the edge and vertex color classes. So in particular, you can generate every RCOP coloring of your graph by taking every subgroup of its automorphism group, taking the orbits and calling those the color classes. So for example, this graph is RCOP. I can get this coloring by, doing the sort of flips within these two triangles, 1 to 2 and 3 to 4, or sending the triangles to each other. So that's these guys. And then I can also send 7 and 6 to each other. Okay. So these are the color classes. Here's a not RCOP graph. So I did a couple of things here that ruined the RCOPness. I colored this guy gray, but that's a problem because I need to be able to send this blue vertex to another blue vertex. 5 would be fixed, and I'd have to send this edge to a red edge. And also, similarly, I colored this, this 6 is blue now, but I need to be able to send this black edge to a different black edge, which wouldn't line up with the vertex color classes. So it's a pretty restrictive condition. The name RCOP is not very informative. In this paper, they introduced a couple of other types of like symmetry restricted models. So there were RCOR models, which is restrictions on correlations, and RCON models, which is restrictions on concentrations. And then they sort of just named this one analogously, but P for permutation. So that's where the name comes from. It's not super satisfying, but okay. Any questions about the definition?
Sorry, what does it mean if there's no edges?
Then I guess it's any subgroup of the symmetric group. Yeah, so you can, yeah.
I guess
So-
this also includes the case where you don't have any, everything is its own color.
Yes, exactly. When we take an uncolored graph, actually deceptively, we usually think of it as being colored with everything a different color, and so you recover the uncolored graphical model case from taking the subgroup to just be the identity. Great. Okay. So now this block graph condition is a condition just on the uncolored structure. So a graph is, we call it a block graph or a one-clique-sum of complete graphs. If I can partition, this is sort of a recursive definition, so I can partition the vertex sets into A, B, and a singleton C, such that removing C separates A from B, and the remaining things, right, when I add C back in, are either complete or block graphs. It's a little, kind of a lot to digest, but probably a better way to think about it is that you can create a block graph by just repeatedly gluing cliques at a single vertex. So take a clique, pick a vertex, glue another clique to it, take another clique, pick a different vertex, and keep gluing. That's how you get your block graphs. So for example, this one that we looked at before is a block graph. For example, I could take A to be 1, 2, so I'm like separating this clique from the rest of it. B to be everything except for 5, and C is just 5. And so I've really just glued 4 complete graphs along a vertex. This is maybe a little deceptive. I don't need to always choose the same vertex. So I could then take another, K5 or something and glue it to 7 and keep going in a path. Okay, great. So here's some block graph facts, which I already touched on a little bit. So first of all, they're chordal, but they're more than chordal. They have this very special property that if I have any cycle in my graph, then actually the subgroup in the subgraph induced by it needs to be a clique. So also, this is very useful to us. What? Hello.
Okay.
Other people are hearing this too. Great. I'm gonna pause until this.
Enjoy it.
Right, yeah, you should be good now.
Great, okay.
Oh, God.
All right, so, okay, I think I was maybe in the middle of this proposition. So another nice fact about block graphs is that if I have any 2 vertices, there's a unique shortest path between them in the graph. So this is when I said, oh, there's only one way to get from U to V, which Vidit noticed is not true at all in that graph. There's a unique shortest way to get from any 2 vertices. And I'll call this is my shorthand for it, is this U double arrow V. And I'll introduce this notation where I want to record, if I have the shortest path, I'd like to record the multi-set of all of the colors that I encounter along that path. Or at least the colors of all the edges. So I record the multi-set of the color of U and the color of V, and the multi-set of all the colors of the edges along the shortest path. Okay, I'll do an example on this next slide in case this is a little tricky. So this lets us define a monomial map that we call the shortest path map. So I've got an RCOP block graph. In fact, this map could be defined for any colored block graph, but it just won't be very useful unless it's RCOP. Or maybe it will be, I don't know, but not in a way that's visible to me. I'll let capital lambda of G be just the set of all of the colors that I use. And this shortest path map sends the polynomial ring in the sigmas, so in the entries of my covariance matrix, to parameters that are indexed by the different colors that I use. And I send this sigma ij to the product of T given by the color of I, so the first endpoint, and the color of J, and then the product of these parameters for each of the edges in the shortest path from I to J. So just walk along the shortest path and record the colors and add each of those to the monomial. So for example, if I'd like to, okay, I can write down the integer matrix whose exponent vectors whose column vectors are the exponent vectors on this side. For example, if I want to look at what does sigma 1, 4 get, well, I start at a blue vertex, and then I use a red edge, so that's this one over here, and then I use this black edge, so it's this one down here, and finally I land at a green vertex. So that's this one over here. If I take a single vertex, I'll get a 2, right? Because it's the first and last endpoint in the shortest path. Okay. Was this clear? I'm going to have a brief interlude on toric ideals and Markov bases, which is probably going to be familiar to most people here, but just in case, we'll go over this a little quickly. So if I have an integer matrix whose columns are, say, A1 through AN, then this defines a monomial map between the polynomial rings given by the columns and the one with parameters specified by the rows, where each xj gets sent to the product of the t's with the jth column as the exponent vector. And this is a monomial map. So its kernel is a toric variety, or is a toric ideal, and this is the vanishing. Oh, that sentence makes no sense. Sorry. It is the vanishing ideal of a toric variety. Sorry. And here's sort of a important fact about toric ideals. Being toric is equivalent to being prime and generated by binomials. And we get a nice characterization of the binomials that live inside of this toric ideal by looking at the integer kernel of your matrix. So a binomial, say x to the u minus x to the v, belongs to this toric ideal if and only if the difference of these two vectors u and v belongs to the integer kernel of your matrix. So there's another notion that you can define of a Markov basis of an integer matrix. So this is a subset of the kernel, of the integer kernel of your matrix. And it's called a Markov basis if whenever I have two non-negative integer vectors whose product with A is the same, basically what I want to be able to do is use elements of this Markov basis to go from u to v in a way that remains positive throughout. So there's a sequence of basis elements such that u plus these basis elements is equal to v, and each of these partial sums is non-negative. So every time I add one of these b's in, I stay positive. And so the key idea is that a Markov basis allows you to get from one element of a fiber of this matrix to another one while still remaining in the fiber. And these are used in statistics, and we're connected to toric ideals through the so-called fundamental theorem of Markov bases, which is that if I have a Markov basis, this list of vectors in the integer kernel of your matrix forms a Markov basis if and only if the binomials that I get from these generate the toric ideal. So I take the positive part and the negative part of each of these Markov basis elements, and I put them as the two exponents on either side of my binomial, and this needs to generate my toric ideal. So yes?
If you go back one slide, I'm trying to understand. The condition seems to be symmetric in U and V, but the basis is not symmetric in U. So if AU equals AV is perfectly symmetric, but now you're saying so B minus U has to be some sort of positive at every stage. Which means if I flip it, it's not.
So the B's are not necessarily positive. Yeah, in fact, they shouldn't be positive. Yeah.
But it's bidirectional. It's not just one direction.
Yes, totally. It is. You can also go from V to U in this way.
But by using a different V.
Yeah, maybe you might have to use a different sequence. But
Well, like take the negatives of them.
yes. Right.
Okay. So
Yeah. Does that answer your question? Yeah, exactly.
So it's stronger than there's like a way to go to down to like a sink in every fiber. It's stronger than that. It's like the fiber is strongly connected by elements of the Markov basis.
Yes.
Okay.
Cool. So the moral of the story is that generating sets of toric ideals are equivalent to these Markov bases. And the thing to really take away from this is that I can study the generators of this toric ideal by looking at special spanning sets of the integer kernel of my matrix. Okay, great. So here's a big what?
Well, actually, from that, okay. That I mean, from what you said before, if I have a set of generators for the toric ideal, I don't necessarily have the negative of the BIs, but you may need that to make it strongly connected.
Okay.
So I think there's definitely you allow negatives.
Yeah. Yes. Right. So if you take plus or minus these to be able to go back. Yeah. Thank you. Great. All right. Here's the example that we were looking at before. So here's my matrix A printed again. I guess I should really transpose this, but to make it fit on the slide, I didn't. So one Markov basis is this thing. So for example, I have a 1 for sigma 1, 1 and a negative 1 for sigma 2, 2, and that corresponds exactly to the generating set of this toric ideal that I showed you before. So this one corresponds to sigma 1, 1 minus sigma 2, 2. Here I've got, say, minuses for 2, 3, and 3, 4, and pluses for 1, 1, and, or sorry, for 2, 4, and 3, 3, and those are like the either side of this binomial. Okay, so how did this work in the uncolored case? So uncolored graphical models, as we noted before, are actually just special cases of the colored graphical model where every vertex has a distinct color and every edge has a distinct color. And what Pratik Misra and Seth Sullivan showed is that if I have an uncolored block graph, then the vanishing ideal is equal to the kernel of the shortest path map, and so is toric, and it's generated by degree 2 binomials. The degree 2 part isn't immediate from that. One has to show that.
So this is also saying that the shortest path map parameterizes this LG inverse?
Exactly, yeah. And so for example, it's the thing that I was describing before. If I take this binomial, I guess before I'd replaced 1s with 2, but so 1 sigma 1, 4 minus z times sigma 3, 3 minus sigma 1, 3 sigma 3, 4, and I collect the endpoints and the edges of each of these, I get the same multiset. So it's in the kernel of the shortest path map. Great. Okay, so that was helpful to us, but now we need to incorporate this coloring, and we can do this by defining a special completion of our colored graph. So if I have an RCOP block graph on n vertices, if a connected RCOP block graph on n vertices, then I can define its completion as follows. So it's obviously a complete graph on n vertices, and the way that I color the edges that I've added is I let 2 edges be the same color, if and only if the shortest path between between its endpoints use the same color. Right, so basically defining it to be to vanish on the shortest path map. So for example, here 1 to 4 and 2 to 4 use the same colors when I go between them, and so I add this edge in with the same color. One could actually define this. This doesn't need to be only defined for a block graph. You could define this for any RCOP graph. By just taking the automorphism group, or the subgroup of the automorphism group that you use to get the color classes and extending that action to the complete graph, and letting the colors be the orbits, or the color classes be the orbits. But indeed, one needs to prove that those are the same by checking that you can send any shortest path to any other shortest path in an RCOP block graph, which is true. Okay, so what we showed is that if I've got an RCOP block graph and its completion, or indeed any RCOP graph and its completion, then the inverse linear space is actually exactly equal to the linear space that you started with, which is very unusual. And so hence it's toric and generated by linear binomials. So for this we needed to use the theory of Jordan algebras. So the linear space associated to this completion actually forms a Jordan subalgebra. And this implies that it's equal to its own inverse linear space, which is a result of Jensen. And thus, that if they have the vanishing ideals generated exactly by these binomials where the colors used on either side are the same. Okay. And each of these linear binomials belongs to this kernel by construction. In fact, there's something stronger that we showed, which is that if I have a colored complete graph on n vertices, then this linear space is a Jordan subalgebra if and only if the graph is RCOP.
Can you go back? I have very confused with the complete and complete.
What is the?
This color complete graph, and then if and only if KN is complete.
Oh, sorry, RCOP. That is not the word that's supposed to be there. I just blanked. Sorry. If and only if it's RCOP. Sorry.
The completion is always complete.
Yes.
The completion is always complete and RCOP. Yeah.
Okay.
So by taking the same subgroup that you use to get the color classes, but as a subgroup of SN for the complete graph.
So does this suggest that your proof strategy will only work in the RCOP?
Yes. And yeah, so that's actually a conjecture that actually if you're not RCOP, then you're not going to be toric. At least we don't have any examples of that ever happening. Okay, so now we know all of the things that we need to really understand the main theorem. So I'll let BG, like uncolored G, and B completion of the colored graph, be generating sets of the two ideals. So for this one, these are binomial generators in the uncolored ideal. So I only have such a binomial if the multi-set of edges that I use on the shortest path from I to j and k to l are the same as the multi-set of edges that I use on, or sorry, u and v, from I to j and u to v is equal to that used from I to v and u to j. And then similarly for this one, I have this generating set just by the linear binomials given by the colors used along the two paths being the same. And so what we show is that this vanishing ideal for the colored graph is equal to the kernel of the shortest path map, and the union of these two Markov bases or these two generating sets is a generating set for the ideal. So the proof strategy is as follows. First of all, it's clear that we have this containment of linear spaces. So the linear space given by the colored graph is contained in that of the uncolored graph and that of the complete graph. And that gives us the reverse containment of ideals. So you get the same containment of inverses and then the reverse containment of ideals. The hard part is showing that the kernel is indeed the sum of these two ideals. And that's using this Markov basis stuff. And finally, so we have this containment and their dimensions are equal. And so since they're both prime, two ideals are equal to each other. So that's sort of the proof strategy. What does it mean to have something in the kernel of the shortest path map? Okay, so I have some binomial. It's in the kernel of the shortest path map. So maybe I'll write this as like capital L minus capital R. And so in order to be in the kernel of the shortest path map, it needs to be the case that the multi-set of all colors used in the union of all of the paths on this side needs to be equal to the same multi-set, the union of all of the paths on this side, where each of the unions is taken as a multi-set. Okay, so that's what it means to be in the kernel of the shortest path map. And then how do I show that something that I've got a generating set or a Markov basis? Well, it needs to be the case that, so for in this example, that if this condition is satisfied, then I can get from one set of paths to the other set of paths by doing one of two things. So the only two things that I'm allowed to do is either replace a path from I to j with a path from, say, I prime to j prime, such that the colors that are used along them are the same. So in other words, this is using a Markov move that comes from this linear ideal from the completion, or I can replace a pair of paths, say I to j and k to l, with another pair of paths I to l and k to j that use exactly the same edges. So now not taking colors into consideration, but really the same edges in the graph. So claiming that this is a Markov basis for the ideal means that one has to show that I can use these two types of operations to get from one set of paths to the other set of paths. Okay, so you can do this just for a little example. So here's a cubic binomial that is in the vanishing ideal for this graph. And I want to get from this collection of paths, so 2 copies of the path from 1 to 4, and 1 copy of just 3, 3 itself, to this collection of paths, 2 to 4, 2 to 3, and 3 to 4, using only these Markov moves. So what can I do? So here's sort of a visualization of these. Here's 2 copies of 1 to 4, and here's 3. And I can replace 1, 4 with 2, 4, or sorry, yeah, 1, 4 with 2, 4, to get twice, so to get both of these guys. So that's using one of these linear binomials. And now from that, I can take 1 copy of 2, 3, of 2, 4, along with 3, 3, and replace that with the path from 2 to 3 and 3 to 4 on this side. So that's 2 to 3 and 3 to 4. So this uses 1 linear binomial and 1 quadratic binomial. Great. Okay, so I promised a little bit about non-block graphs. So what the topic of continuing work with Aida Marai, and we also proved this with Hal Schenk, is that, so I don't get this same sort of thing for non-block graphs, but I at least get a minimal prime. So if this script G is an RCOP block graph, whose underlying uncolored graph is this regular G, and its completion is G bar, then at least the ideal I'm interested in is a minimal prime of the sum of these 2 ideals. Okay, so before we had a toric ideal, and so it ended up being prime, but in general, that's the result of taking the sum of these 2 ideals is not actually going to be prime. There's going to be some extraneous components. So for example, here's a graph that is not a block graph, and I have 2 different colorings of it, and sort of interesting, the subgroups, right? The subgroup here is just just sends 1 to 3 and 3 to 1. The subgroup here just sends, that flips 2 and 4. So they have the same, same size subgroup, lots of, but it's, so in this top case, so what do I want to say? Yeah, okay, so here are the two vanishing ideals that I get. But the other thing to note, which I guess I also should have written, is that in this top one, it really is just the sum of these 2 ideals, but in this one, I need to take a minimal prime. So equality can fail, and these can look fairly different.
So they're not toric.
No, they're not toric.
But they are RCOP.
They are RCOP. So I think this is only like looking at this completion doesn't make sense if it's not RCOP is a thing. So I wouldn't, if you gave me just any old colored graph, I wouldn't actually know what this completion should be to add it. Yeah. But you'll notice that we still have the linear binomials that you would expect coming from this IG bar. Okay. Okay. So what are some future directions? So I guess first of all is something that I touched on briefly, is are there any non-RCOP or non-block graphs whose ideals are toric? I don't think so. If you can think of an example, I'd be really interested to hear about it. But I've done a lot of looking and I really can't find one, so I think it's not true. But you also might ask, what about after a linear change of coordinates? And then there are definitely good examples where they're not, Of non-RCOP graphs where they're toric after a change of coordinates. So here's one, for example, definitely not RCOP because these two edges have the same color, but these two vertices don't. And as expected, its ideal is this. So it's got this 4-term quadratic that I can't reduce down to a binomial. However, I have this like really easy change of coordinates. I let Pij be negative sigma ij for all of them except for 2, 2, and 2, 3, which get these. And then I get something that is quadratic and toric. And there's one, if you had like a star with all different colors, the same type of thing would work. And there's more general, but sort of small cases that we can think of. But it'd be really nice to get like a more unified theory for when there is a linear change of coordinates that would give you something toric. Here's a good, I will advertise this work by Marai and Powell very recently. They have a nice way of certifying that something is not toric after a linear change of coordinates. So they use symmetry-Lie algebras for this. And in fact, in this paper, they applied their techniques to an uncolored graph of the 4-cycle to show that is not toric after any change of coordinates, which I think that probably everyone in algebraic statistics suspected, but that we didn't have a proof of. So that's a nice application of this. It doesn't always work. The answer it gives you is always true, but it might not be able to certify that something that isn't toric actually isn't, because it's comparing dimensions of certain.
It's like comparing like tangent spaces and not the whole group actually.
Yeah, exactly. But it's nice if you have a case where it works, and it's been useful in this direction already for these uncolored models. So I think this is a nice work in this direction from recently. And then finally, you can ask things about ML degrees and MLEs, especially for like non-RCOP colors and non-block graphs. Can do the same type of maximum likelihood estimation questions. And okay, great. So with that, I guess I'm a little bit early, but there's plenty of time for questions. So I want to say thanks very much to the organizers of this workshop for the invitation, and thanks so much to all of you for listening.
Thank you, James. Questions?
Yeah, so the reason I asked earlier, so when there's no edges in the graph, then you're basically looking at the inverse of a linear space, right? Because now you have diagonal matrices, so all inverses will be diagonal. You're looking at a reciprocal linear space. Are there examples there? I mean, is it clear there that there are no other inverse or reciprocal linear spaces that are toric except the ones that are their own reciprocal?
Well, for that, everything would be RCOP, right? So they would, right, is that true?
Yeah.
Yeah, okay. Yes. But also, so that's just for like equalities among the entries, but there is also like another project that came out of this LSSM thing, did this talked about this for more general diagonal linear spaces. There's also work by David Spire and one other person about this. Oh, I can't remember. Frank, do you remember?
No. I'm just laughing because it's really, you're lucky the other person is not here.
Oh, okay.
I was once the other person when you're about talking about a result. It was kind of funny.
Yes, sorry. It's from a while ago, so I sorry. I have it somewhere in this computer that I can send to you, where they also talk about this.
So
Proudfoot.
Yeah,
So they
did the
Got it.
ideal of the reciprocal linear space, right? So this is by a circuit of the matrix.
Yeah, exactly.
I was just wondering if in that case it's known.
Yeah, I think that case is really well studied.
Other questions? I have a high-level question, which is, so toric is good, not toric is not good. So tell us the kinds of things you want to do if the model turns out to be toric that are impossible if it isn't.
Yeah, I guess I wouldn't say impossible about anything necessarily, but I really think like this
More difficult.
this MLE, I don't know why I'm scrolling all the way back, but this MLE stuff I think becomes really nice when things are toric. So counting number of critical points of the likelihood equations is and especially finding a closed form. And there's some nice cases where actually like if it was toric, that the like log linear MLE is basically the same thing as the Gaussian MLE. So this is the case for like reciprocal ML degrees for Brownian motion tree models. So those are linear in the covariance. There's a whole there. Yeah. But so that happens there, and I suspect could happen more generally in other cases. So that would be really nice to be able to like port in a lot of the things that we know about log linear models into this. That's one example.
Well, I mean, toric varieties, there's 3 classes of varieties. There's linear spaces, toric varieties, and everything else. and that's the consequence of this binomial ideals result. And so
Yeah,
it's
well, I
rather
think you want
remarkable.
to say Chebyshev varieties,
Yes,
the new
there are all kinds of
toric
other
variety.
Yeah, I mean, you also get like, I love polyhedral geometry, so like I would love if any problem can be reduced down to polyhedral geometry, and obviously like just by computing the volume of this, you get an upper bound on the ML degree, so things like that.
But you don't yet know which RCOP models are toric. You know some that are.
I know some that are, and
Some that aren't.
some that aren't, but yeah, mostly that's wide open. So I think it's. Yeah. I mean, I think these are all of them. I think it's just block graphs. That's the conjecture,
I see.
but technically we don't know.
So speaking of these, you mentioned again the MLE, ML degree. So these RCOP block graphs are all ML degree 1.
Mhm.
And what's the MLE? Like the expression? Can you express it also in terms of the cliques somehow, like in the uncolored case?
Yes, and it's in this paper. It should be in the reference. It no, it's not in this paper. It's in the paper by another paper by Lauritsen and Gehrman. They talk about and they also do it for not mean 0, so they estimating the means and the covariance matrices. I don't remember exactly what the formula is, but it is in a paper by those people.
Okay.
Any other questions?
I once talked to Aida about these changing bases to make it toric. Is there a good algorithm for that by now, or?
The algorithm is Ask Aida. Yeah, she's really good at like looking. I think she's got a lot of practice like looking at it and really just being able to see it. But no, not that I know of. I mean, yeah.
I mean, the work with RCOP, JM asked a question of Aida, and then they realized it's possible to actually do something, but it's not an algorithm. It just tells you when you can't do it.
Yeah.
I think it's kind of hard. People would like there to be an algorithm. But
Yes.
You basically have to compute the isomorph. You have to compute the automorphism group of your variety and show that it has a maximal torus that acts linearly or something.
Yeah. So yeah, right now that's sort of the thing. Like this is very ad hoc. It was found in like we just tried stuff and we found the change.
You can eyeball it almost.
Yeah, exactly. And and then there's we have like a couple of more general classes that you just try hard enough, you find it. But yeah, we don't have a good algorithm.
But even something that says yes or no.
Right. So this thing says no,
Some of the
but some of the time. But yeah, nothing yet that says yes.
And Aida says yes some of the time.
Yeah, and Aida says yes some of the time, and those are the two most effective tools that we
Well, I
have.
mean, this whole process, people keep finding varieties or models that our toric interchange recorders is incredibly fascinating.
Mm-hmm.
And I don't work in it, but I'm really surprised to see all these.
Yeah, it's interesting how much it comes up. Yeah.
Great. Any last questions or comments? Good. Then let's thank Jane again.